So the definition of neighborhood says that if you choose any point x naught inside the real axis, right, then the neighborhood of that point is defined as the small interval of epsilon radius, where x naught is considered as the centered point, right? So mathematically it is denoted by these symbols. It means that neighborhood, n means neighborhood of the point x naught having the radius epsilon is actually equal to the interval which is of width 2 epsilon. If we compute the width of this interval, that will come out to be 2 times of epsilon, right? So x naught is taken as the center of that interval, right? And if you want to see the picture, then this is a picture of neighborhood of any point. This is the point, this red colored dot is the point x naught chosen on the real axis, right? And you can see that the radius on the both sides of this x naught is epsilon, left as well as right, right? And it is taken as the open interval. You cannot choose a closed interval, because if you want to choose a closed interval, then in that case you will be able to locate this position. I mean, this point could be located x naught plus epsilon, and that will eventually give you the value of numerical value of epsilon, which is not possible, because epsilon is just a positive number which is as small as possible, which is as small as you please, right? So these brackets has to be open brackets. You cannot make them close. Okay, right. Now the open set. So open set, the definition of an open set, if you choose a set capital X, which is a subset of R, right, then it is said to be open if every neighborhood of each point of that set X is contained in X, right? It is not like that any point of the set capital X has a neighborhood which doesn't fall inside capital X. Every neighborhood of any point of this set should fall within capital X. This is the requirement, and if it happens, then we say that the set X is open, right? And here you can see the real life example of an open set where X is a family having 3 members: father, son X, and son Y, right? And suppose there is a girl alpha which comes in the neighborhood of son X, which is of course one of the member of the family, right? And this, if this neighborhood of x, which can be written in this way, neighborhood of x within the radius epsilon, right? If this neighborhood is accepted by the family x, right, then we can say that the family is open, at least for the son x. And if this happens for son y also, which actually possess this girl beta in his neighborhood, right? And if this neighborhood of son y is accepted by this family, then of course this family, this set X, will be called an open set, at least for the son Y. And same should be true for the father, right? So if father is having some friend, right, and that friend is accepted by the 2 sons, right, then we'll say that the neighborhood of the father is also absorbed by the set X. And in that case, you can say that for each of the member of the family, their neighborhoods always belong to the set capital X, and then you can say that the set capital X is an open set, right? Okay, and here you have written this R. R in this example is actually the set of all humans, right? So because X is a subset of R, okay? So this family is a subset of a set of humans, of course, right? And in order to say that a set is not open, you just need to locate an element of set X whose neighborhood is not contained inside the set X, right? So you just need to pick up that specific element for which the neighborhood doesn't belong to the set capital X. Then we say that the set is not open. And please note that a not open doesn't imply closed. Closed and open are not opposites of each other, as you generally use in English language, right? A set may be both open as well as both closed. There are sets which are both open and closed, and there are sets which are neither open nor not closed, right? Okay. Now, here are some examples which will help you to understand why some sets are open and some are not open. Like you see the example of a set of integers It is not open because if you pick any integer, think about integers, and you pick any integer, suppose you pick 1 and just draw the neighborhood. Neighborhood is something like this, a small band of width to epsilon, right? You have to draw a small band of width to epsilon around 1 like this is 1, and a small band of uh, radius epsilon, right? And you can see that the points falling in the neighborhood of 1, right, will not be belonging to the integer set capital Z, right, because there will be actually real numbers which will fall on the left as well as on the right of 1. You have chosen epsilon as the least positive distance. Note that epsilon is something which is very less, very close to 0, but not 0, right? So the neighborhood of 1, this is the way how you write the neighborhood of 1 with the epsilon radius, which will be an open interval 1 minus epsilon to 1 plus epsilon, that will not be belonging to the set capital Z, right? And for the same reasons, the set Q of rational numbers, that will not be open, because if you pick any rational number, suppose you pick 10, then the neighborhood of 10, that will be denoted by this open interval 10 minus epsilon to 10 plus epsilon, that will contain irrational numbers, right? And of course, in that case, this neighborhood cannot be subset of the set of rational numbers. The problem is that any real interval you choose, no matter how small it is, right? If you pick up any real interval from the real axis, it doesn't matter how small it is. It always contains irrational numbers as well as rational numbers. You cannot just separate rationals and irrationals. They are mixed thoroughly, that you cannot separate them. Nobody can pick an interval from the real axis containing only rational numbers or containing only rational numbers. That if you pick any interval, then it will be having rationals as well as irrationals, right? So there is no chance that this interval will be a subset of set of rational numbers, because this is having irrational numbers also, right? Okay. Now, same is the reason for the set of irrational numbers, that will not be open for the same reasons. And you can see that this is an open interval, and open intervals are generally open, but not because of the reason that they are having this kind of brackets at their ends, but due to the reason that is furnished by the definition of an open set. I mean, you should apply the definition of an open set here in order to see that why it is open, right? You can see that for any point belonging to this set, pick up any point inside the open interval 0, 1. Suppose you pick the 0.5. This is the midpoint of this set. So generally people pick up the middle point. So I have picked the same 0.5, and you draw a small neighborhood of 0.5, epsilon distance towards the left and epsilon distance towards the right. Then you can see that there are so many real numbers in that small intervals, and all of them are belonging to this set capital X, right? And if you pick any number other than 0.5 or other than 1 and 0, right? You cannot pick 1 and 0, because 1 and 0 are not the members of this set, right? So be aware of this thing. You are going to pick any real number between 0 and 1, and you can see that if you draw a neighborhood around that chosen number, that neighborhood will completely lie inside this capital X. There is no chance that that neighborhood will go beyond these boundaries 1 or 0. That's not possible, right? Unless and until you pick up the endpoints 1 and 0. But unfortunately, you cannot pick 1 or 0, because 1 and 0 are not the members of this set, right? So the neighborhood should be taken for those points only which are actually the members of the set, right? The points outside the set are of no importance for us. Okay. Now the fifth one, you can see that this is of course not open, not because you can see that there's a bracket, square bracket here, not because of this reason, because of the reason that 1, if you draw the neighborhood of 1, that will be 1 minus epsilon to 1 plus epsilon. 1 minus epsilon neighborhood will lie completely inside this, but unfortunately the right neighborhood of 1, that is 1 plus epsilon, will be falling outside this capital X, right? So you can see that there are so many examples here, and you can apply the same reasoning again and again to see that why these sets are open and why they are not open, right? Okay, now I will move to the limit point. This is another important concept of this topic. What is a limit point? So a limit point is something which is never alone. Isolated persons in the society cannot be the limit point, right? Someone who is trying to be a monk, um, right, cannot be a limit point. Someone who is always involved in the society, right, can be a limit point. So a limit point is something which is which can be seen as a center of attraction. I mean, that is always surrounded by other points. That is called the limit point. A limit point is never left alone, right? If you spot the limit point, then you will see that there are so many points just sticking around that limit point, right? So this is just an intuition about limit point. And what does the mathematical definition of limit point tells us? See, a point alpha, which is a real number, you have to pick that point from the real axis, because we are talking about real axis. This topic actually devotes to the real axis only, right? Though limit point can be found anywhere in other spaces also, but we are only sticking to real axis, right? So you pick up a number alpha from the real axis, and that is said to be the limit point of a set capital X. So you have a set X, which is a subset of R. So that alpha, that should be a real number. Please note that alpha need not to belong to this set X, right? It means that limit point may lie outside the set. That is also possible, right? So if you pick up a number alpha, a real number, and that is said to be the limit point of some set X, if every neighborhood of alpha, if you draw the neighborhood of alpha, you know how to draw the neighborhood that contains the points of X other than itself. That's it, right? It means that alpha should not be the isolated point. In other words, you can say that alpha should not be the isolated point. Alpha should always contain few points, or at least one point of the set capital X, in order to say that alpha is really a limit point. Right? So mathematically, you can say that if you draw the neighborhood of alpha, you can say that this is the alpha and this is the neighborhood of alpha. And if you intersect this neighborhood with the set X, then you will be having something in this intersection. It is not possible that the intersection is empty, because as I said earlier, that alpha is never an isolated point. There has to be some point in the neighborhood of alpha other than alpha, and those points should belong to the set X, right? So you can write this also along with this, that intersection should be non-empty. This is the first condition, and there should exist some y, right, such that y belong to the intersection of the neighborhood of alpha and set X. It means that y is that fellow which is sticking to alpha. It actually means that y is the fellow which is always sticking to the alpha, right? And that's why we can say that alpha is not an isolated point. Alpha cannot be left alone. Alpha has to be with some member of X always, right? And that member is Y. So Y is the member which is always sticking to alpha. That's why alpha can be called as limit point, right? Okay, and the other words we use for it are cluster point and accumulation point also, right? Okay, and another important remark, that limit point need not to be the element of X. It is not compulsory that the limit point alpha should belong to X. Limit points sometimes lie inside the set X, sometimes they lie outside the set, or specifically I should say that they lie at the boundary, right? If they do not lie inside the set, then they always stand at the boundary, right? So this is the behavior of a limit point. Either they lie inside the room, or they will just stand below the door, right? Okay, now there are some examples. So if you consider the real line and you pick up any point from the real axis, right, and if you pick up any point on the real axis and just draw a small neighborhood on its left and on its right, then you will always see that on the little neighborhood of that particular chosen point, you will always find so many points of the real axis. It means that the chosen point cannot be an isolated point, right? There are always some points which are just flocking towards that chosen point. It means that, that every point of real axis is a limit point, right? You cannot choose a point from a real axis that is an isolated point, right? That the chosen point will always be sticking to some other points of real axis. Okay. Right. Now the other example, the set of integers z. So imagine the set of integers, right? So I have drawn the set of integers on the real axis. This black colored double arrow is for real axis, and these red colored dots are for integers, right? And as you can see that I have chosen a particular integer, that is 2, and a neighborhood of this orange color patch is drawn here, right? And you can see that in this orange colored patch, which is actually the neighborhood of 2, uh, there are no integers, right? So since there are no integers in this orange colored patch, it means that this 2 and this 2 is actually an isolated point, right? So it cannot be a limit point. And of course, this is true for every integer you choose on this real axis, right? So neither of the point on the set of integers z is actually a limit point. So there are no limit points inside the set of integers capital Z, right? Now we'll talk about set of rationals. That is very important, right? And that will give you a clue that limit point actually may lie outside the set, right? So it's not like the case that always limit point reside inside the set. No, they may lie outside the set, right? Limit point need not to be an element of that set we are talking about, right? Now think about the set of rationals, right? So as you know that, as I told you earlier, that rationals and irrationals are badly mixed. They're badly mixed in such a way that nobody can separate them, right? So if you choose any rational from the real axis, please note that whatever you choose, whatever you do, you have to be on real axis. Your universe is the set of reals, right? So since we are talking about the set of rationals Q, but you have to choose an element from real axis, right? Firstly, what you will do, you will just pick a rational number. You will just think about a rational number, right? Think of any rational number. Suppose you think about a rational number that is 1 upon 2, and you draw a small neighborhood of this orange colored, right? And you will see that there will be so many rationals inside that small patch, right? Of course, you know that in a small patch of real axis, in any small interval of real axis, there are infinite rationals and irrationals. And of course, you studied that the cardinality of any real interval is absolutely equal to the cardinality of reals, right? So you can say that there are uncountable number of points inside any interval a comma b, right? Now, since you have selected a rational number that is 1 upon 2, or you can say it's zero point 0.5, the neighborhood of zero point 0.5 will be an open interval 0.5 minus epsilon to 0.5 plus epsilon, right? And since this is an interval, it will be containing infinite number of rationals as well as irrationals. Due to the property that it is an uncountable set, every interval is uncountable, right? So it will be having rationals as well as irrationals. Okay. Now, since it is having other rationals other than 0.5, it confirms that 0.5 is a limit point. Note that a number is said to be a limit point, right, if it is not isolated. So the interval 0.5 minus epsilon to 0.5 plus epsilon, which is an interval and which is actually the neighborhood of 0.5, is actually containing other rational numbers other than 0.5. It proves that 0.5 is a limit point. And of course, you can say that every rational number is a limit point of this set, because if it is true for 0.5, it has to be true for 0.4, 0.3, 0.2, etc., etc. Any rational number you choose, this property will be true for every rational number. It means that for the set of rational numbers, every rational number is a limit point, right? Okay. So far we have proved that the elements of Q which actually lie inside Q are the limit points. But what about the elements which do not lie inside Q? Is it possible that an element which is not lying inside the set can be a limit point. Yes, it's possible, because as I said earlier, that an element which is not lying inside the set, which is standing at the boundary, can be a limit point. Now, what are the points which are not lying inside the set of rationals? Yes, those are irrational numbers. Now think about any irrational number like square root of 2, right? And just make a small neighborhood around the square root of 2. That will be an open interval, root 2 minus epsilon to root 2 plus epsilon. Right now, see, this small interval is again an uncountable set, right? And this will surely be having rationals as well as irrationals, because nobody can separate them, right? It means that root 2 is not an isolated point, because root 2 is containing rational numbers other than root 2, right? Of course. And so we can say that root 2 is also a limit point, because it is not isolated, right? It means that every irrational number should be a limit point. Okay, so you proved that every rational number is a limit point of Q, and every irrational number is also a limit point Q. So summarizing this, we can say that every real number is a limit point of Q. And this is very, very important. You should think about this set again and again, and you will realize that the concept of limit point is somewhat very abstract actually, right? Okay, this is a very good example. Now, the set open interval 0 comma 1, you can see that the fourth uh, example 0 comma 1. Now, every interior point, I mean that the point belonging to this set. You can see that the point 0 0.1, 0 0.2, 0 0.3, all these points are belonging to this set. Right? Okay. Now, every point which is a member of this set, right, will be a limit point by the same reasons. If you draw a neighborhood, a small neighborhood, think about a small neighborhood around that point, and that neighborhood will be containing infinite number of points of this set, right? Because until and unless you choose a single point, that interval will always be having infinite number of points. This is the beauty about real numbers, right? No matter how small you choose that interval, there will always be an infinite number of points, right? Okay, so every real number inside this set will be a limit point, right? But think about the number, this number, boundary number 1, right? If you draw a neighborhood at 1, please note that 1 is not the member of this set X. If you draw a neighborhood of 1, that is 1 minus epsilon to 1 plus epsilon, then you will see that the left neighborhood, that is from the, that is the set, if you consider a half set from 1 minus epsilon to 1, right? So this is just the half of the whole neighborhood, right? So this part is having infinite number of real numbers belonging to this set. It proves that 1 is actually not an isolated point, right? 1 is sticking to infinite many points of this set X. Similarly, this point 0 is sticking to infinite points of this set X, though 0 is not the member of this set, right? Yes, Aman Kotnala, you want to ask something? Please ask.
Yes, sir. Sir, actually, I
Hmm.
was having doubt in this particular section about 0 and 1 being the limit points of the set.
Okay.
Sir, because in the definition of limit points, it was clearly mentioned that each and every point, every neighborhood of
Hmm.
that number should be present in the
Yes.
set. So, but
Yes, of course.
considering the equation that
Hmm.
neighborhoods are x naught plus alpha and x naught minus alpha,
Yes.
so the terms x naught 1 plus epsilon naught won't be in the
Hmm.
set of 0 to 1 open interval.
So the half neighborhood is not belonging to, but the left half is belonging to, na?
Sir, but
Belonging to this.
according to the definition, we have to, it's specified that every neighborhood must be there.
Yeah, but neighborhood is a kind of symmetric set, na? The point you are talking about, one should be the center of that neighborhood. First point is that. Okay.
Yes, sir.
Every means for every choice of epsilon. Every doesn't mean that you can split your interval into 10 equal parts. No. Are you getting my point? Every
Sir, but
means
the
for
thing is,
every choice. Huh?
sir, the width of the neighborhood is 2 epsilon naught, but we are getting
Yes.
only the one, the other part of the epsilon naught, that
No
is
problem.
1 minus
But
epsilon naught.
but only the half of the interval, half of the neighborhood is containing infinite number of points of set. Is it yes or no?
Yes, sir, that's true, sir.
no matter how small you choose that epsilon, the left half of that interval, the left half of that neighborhood, that's from 1 minus epsilon to 1, that will be always containing infinite number of points of set x. Is it fine?
Yes, sir. That's fine,
So
sir.
every means for every choice of epsilon. Suppose you choose epsilon equal to 0.0001, right? And
Okay.
sometimes you may choose epsilon equal to 0.00000001, and then it
Yes,
will
sir.
give you two intervals, right? So it will give you two neighborhoods, right? And both of these neighborhoods, whether you choose epsilon equal to 0.0001 and or whether you choose epsilon equal to 0.5 times 01, every time the interval, the left half of the neighborhood will always be containing some part of x, and this is also true for 0, where the right half of 0 will be having some part of x. So every means for every choice of epsilon. Every doesn't mean that you are going to split your neighborhood into 10 equal parts. उसका वो मतलब नहीं है.
Okay, sir. So should we make a change in the definition of limit?
No, 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 absolutely no. कोई जरूरत ही नहीं है उसमें करने की. क्या कोई कंफ्यूजन ही नहीं है उसमें. क्यों चेंज करना है?
So an addition that even a symmetric
Hmm.
half, if it's present, then we'll consider it as a limit point.
Of ऑफ कोर्स डेफिनेशन में यही तो लिखा हुआ है कि अगर जो भी उसका इंटर जो भी नेबरहुड है उसमें कुछ ना कुछ एक्स का हिस्सा आना चाहिए. ये कहाँ लिखा है कि लेफ्ट में नहीं आना चाहिए, राइट में नहीं आना चाहिए? हमने कहा कि नेबरहुड के अंदर कुछ ना कुछ हिस्सा सेट का आना चाहिए. ये अब दाएं से आए बाएं से आए वो एक अलग बात है, ऐसा कुछ बताने की जरूरत भी नहीं है. क्यों?
Okay, sir.
डेफिनेशन में इतना तो लिखा है कि नेबरहुड में सेट का कुछ ना कुछ हिस्सा आना चाहिए. यही तो लिखा है कि नॉन एम्प्टी इंटरसेक्शन होना चाहिए. क्यों? और ये भी लिखा है कि कुछ ना कुछ एक पॉइंट ऐसा होना चाहिए जो उन दोनों के इंटरसेक्शन में आ जाए. लेफ्ट और राइट का तो कोई रोल ही नहीं है इसमें. लेफ्ट राइट तो हम आपसे बात कर रहे हैं जानबूझ के, जिससे आपको क्लैरिटी आ जाए कि किस तरफ से वो कवर कर रहा है एक्स को और किस तरफ से नहीं कर रहा है, राइट? हालांकि इंटरवल में लेफ्ट और राइट जैसी कोई चीज है नहीं वैसे देखा जाए तो. क्यों?
Okay, sir. Yes, sir.
हाँ. ओके ओके अमन.
Thank you, sir.
नाउ ओके वेलकम. Now there are other examples too, which tells you the details about limit point, right? You should go through all these examples. Now the next point, yeah, we talked about adherent point also, right? So what is an adherent point? Adherent point is very similar to the limit point, but there is only one difference, that the adherent point should be the member of X. So this is a strict criteria, right? It means that a point falling outside the set cannot be an adherent point, but it can be a limit point, because as we saw earlier, that limit point may lie outside the set, right? But an adherent point cannot lie outside. Adherent means adhesive, चिपकना, राइट? तो उससे निकला है चिपकता जो है, बिल्कुल एडहेयर करता है, छोड़ता नहीं है. तो सेट से चिपका हो वो जरूरी है. उसका इंटीरियर पॉइंट हो ये जरूरी है इन ऑर्डर टू क्वालिफाई एज एन एडहेरेंट पॉइंट, राइट? और बाकी सब डेफिनेशन सेम है. नेबरहुड ऑफ द एडहेरेंट पॉइंट ऑलवेज कंटेन सम पार्ट ऑफ एक्स. जो पहले था वो भी अभी है, सिर्फ एक ही डिफरेंस है कि जरूरी नहीं है कि वो सेट का मेंबर हो. तो इसका मतलब ये हुआ कि एवरी लिमिट पॉइंट cannot be an adherent point, but every adherent point is a limit point. This is very important. Every limit point is not an adherent point, because sometimes limit point fall outside the set, but every adherent point is the limit point, because adherent point में वो सारी बातें होती हैं जो limit point में होती हैं, लेकिन limit point में एक बात अलग होती है जो adherent point में नहीं होती है. तो आप समझ जाइए किस तरफ से सच है, right? Okay. Now we'll talk about our real axis. You can see that every point of real axis is an adherent point as well as limit point, because fortunately all the points which are the limit points of R are actually lying inside R. That's why we can call them adherent point, right? But that is not true for the set something like this. If I take this set something like this, 0, 1, right? So 0, 1 is a set. You can see that every point lying inside this set is a limit point as well as a adherent point. But if I talk about 1, then 1 is a limit point but not an adherent point, because 1 is not the member of this set X. Okay. Now, so here's a small difference between adherent point and limit point. And now if you collect all the limit points of a set X, right, and you form a new set that's called a derived set, right? So the set of all limit points is called a derived set. Okay, and it is denoted by x prime, x dash, right? So if you find all the limit points of set R and you collect them in a set, then you know that that will be the whole of the real axis, because as I told earlier that all the points of real axis are limit points, right? Any point you choose on real axis and draw a small neighborhood, right? Then that neighborhood will always contain a real number other than that center of that neighborhood, right? So that's why the derived set of R will be absolutely equal to R, right? Okay. And if you choose this set, this is an open interval. You can see that this is an open interval. If you find its derived set, then apart from the real numbers lying inside this set, they are, of course, they are limit point, but these boundary numbers are also the limit points. As I told you that numbers standing on the boundary of a set are good candidates of limit point, right? That's why x dash is equal to the closed interval 0 comma 1, right? Okay. And if you find the limit point of set of integers, you will see that if you choose any integer and you draw a neighborhood around that integer, then you will find no integer in that neighborhood, right? It means that the set of integers doesn't possess any limit point. It means that the set of limit points of set of integers will be an empty set. So the derived set of z will be empty, right? And same is true for set of natural numbers, right? And what about Q? If you find the derived set for set of rational numbers, as I told you earlier, the rationals and irrationals are badly mixed, right? So it proves that we also proved that, and we talked about that, that all real numbers are limit points of set of rationals, right? It means that the derived set of Q will be equal to R, right? And similarly, the derived set of irrationals will be equal to set of reals, right? And here are other examples. You can see that this is set 1 upon n. It will be having numbers like 1, 1 by 2, 1 by 3, 1 by 4, and so on. All of these numbers will be tending to 0, and there will be a huge crowd near the number 0, right? You can see that the denominator is getting bigger and bigger, and they're tending towards 0. So 1 upon infinity tends to 0. So that's why 0 is the kind of limit point, right? And there will be a crowdy situation around this point 0, right? So if you pick up this element 0, and please note that 0 is not the member of this set. 0 is not the member of this set. Note this point, right? If you pick up 0 and you draw a small neighborhood around 0, something on left and something on right, then the right neighborhood of 0 will always be having a crowded place. It will be a crowded place having infinite numbers of the form 1 upon n. N is very, very large, right? Like 1 upon 10 lakhs, 1 upon 10 crore, something like this, right? So the right neighborhood of 0 will always be containing some members of x. That's why 0 is a limit point, right? No matter how small you choose your epsilon, right? It doesn't matter actually, right? There will always be some number which will be sticking to the 0 from right, not from left, because on the left of 0 there will be negative numbers, and this set is not containing negative numbers. Okay, so the derived set of this set will be having limit points of this set, but as you saw that 0 is the only limit point of this set. The crowdy situation is happening only at the point 0, right? No other point can be a good candidate of a limit point. So the derived set will be having the same singleton set, that is element 0. Okay, now closure of a set. What is the closure of a set? So closure of a set, intuitively, closure of a set is something which a set actually tries to stick with it in order to have its all of its limit points with that set. So suppose x is a set, right? And x dash is its derived, right? You know that limit points sometimes may lie inside the set, sometimes they may lie outside the set. So in order to bring all those limit points together with the set, what we do union of x with its derived set, and that's called the closure of set, right? In some sense, it becomes closed, right? If it is missing its limit points, which may lie outside the set, then it tries to bring them together. It tries to tie them together. This operation is actually tying the set with its derived set. Okay, so derived limit points are something like favorite members of the set. You can think like this. Limit points of a set are those points which are kind of center of attraction, something like an infant in a family, right? So you know that an infant in a family is never left alone. That is never isolated. And this is the property of a limit point. A limit point is never isolated. It cannot be left alone. Similar to the situation that in a family X, an infant cannot be left alone. So an infant is always a limit point. A family always try to uh, bring that infant along with it, right? So this is how closure of a set X is made, right? So closure of X is union of set X with its limit points. Okay. Now, if you find the closure of a set of real numbers, you know that if you use this formula, R union R dash, R is R, and R dash is the derived set of R, and you saw earlier that R dash is equal to R, so R union R will be equal to R, right? And the same logic you can apply for these examples also. Now, the closed set. So closed set is something which doesn't misses out its limit points. Something is called closed, which has tendency uh, to get squeezed. Something like the phenomenon of surface tension, like you see in water drop. You know that a water drop is always trying to get a spherical in shape. Why? Because there are surface tensions on the surface of the tiny drop, which actually pull the surface molecules towards the center so that the water drop acquires a spherical shape, right? So this is a tendency of getting close. This is something what we are talking about, a closed set. A closed set always tends to attract and tend to get smaller and smaller. But it is possible only if there are attractive forces which actually pull the set towards the center, and that is also only possible if you bring those limit points inside the set. So if any of the limit point is lying outside the set cannot possess a tendency to get squeezed, just like the water molecule due to the presence of surface tension, right? So what you need to do in order to define a closed set, you need to contain all the limit points of that set inside that set, right? So a set capital X, which is a subset of R, is said to be closed if it contains its all its limit points. Because if all the limit points are contained in set X, then of course set X will have a tendency to get squeezed and to get smaller and smaller in size. That's why we'll say that it's closed. Are you getting my point? Why this word is associated with this set, in what sense, right? So if all the points of attraction, which are called limit points, are present inside the set, there is no chance that a set will just expand. No chance. It will always contract, right? Okay. So closure of or in other words, you can say that a set capital X is closed if its closure is equal to the set itself, right? This is very strange, and of course it is correct that why we call a set capital X as a closed set. Why? If you find its closure, if you find the closure of that set and you find that it's a set itself, it means that closure of a set is not bigger than the original set. It means that the set is already closed. And if the closure of a set is bigger than the original set, it means that some of the limit points were falling outside the set. Think about the physical phenomenon of surface tension inside a spherical water drop, right? Why do a water drop tends to get spherical in shape? Due to the presence of surface tension, which always pull the surface of the water molecule towards the center, and that's why it takes the smallest possible surface area. You know that by geometry, that mensuration, that surface area of sphere is minimum, right? So that's why in order to minimize its size, right, in order to minimize its size, the pull of the attraction, the force of attraction should lie inward, not outward, right? And if you find the closure of a set, and that is actually the set itself, it means that the limit points of that set were actually lying within the set, not outside the set. That's why they are tending to maintain the shape of that set, right? Okay, so R is closed, yes or no? You can follow this definition. If you find the closure of R, then of course a closure of R will be equal to R due to this reason. Since closure of R equal to R, so you can say that R is closed. Or in other words, you can say that there are no limit points of R which fall outside R, right? So that's why R is closed. Similarly, Q is not closed. Why? Why Q is not closed? One way to do this is this C number, reasoning number C, that if you find the closure of Q, that will not be equal to Q, rather that will be bigger than Q. It means that some of the limit points of Q were actually falling outside Q, right? And of course it's true, because irrational numbers are the limit points of set Q and they do not lie inside Q. So that's why Q cannot be closed. A set is said to be closed if it possesses all its limit points inside it. If any limit point is falling outside the set, then we'll say that it's not closed, right? And you can apply the same reasonings on these sets also, right? So is it clear to all of you? This is a kind of revision which I wanted to आप सभी के लिए